Hey, here's something interesting to do with differential equations. I've got a question here for you. In green, what if you can't do it? Okay, what if you can't do what? What if you can't integrate the function? What do you do then? If you can't actually integrate it, I don't know what your chances are of doing this one. There are functions that aren't integrable. And Euler, and just notice how you say the person's name up there. It's not Euler, it's Eulers Method. Euler's method is an interesting little method of what's called numerical integration. Okay, so we're not going to get a graph as such, as with a slope field. We're not going to be able to directly integrate it and get a function. We're going to do something else. So it's an exciting idea, and looking around the screen, I think you can probably see that it's got something to do with tangents here, this method, and this little set of tangents represents our estimate of the position of the actual function that gave rise to the derivative, the differential equation. And instead of integrating back, we're going to try and plot a good estimate with the numerical values, if you like, of the function at various, or estimates of the numerical values at various x values. So, and the same thing over here, going to try and estimate where the function should lie based on its tangents. How do you do that? Well, come down and let's have a look at what Euler did. And this is the idea here. So Euler's method is a numerical method. It gets a set of numbers for the value of the function, or estimates a set of values of the function for various values of the variable. Okay, so we're going to draw a tangent to the curve and then estimate what the function should be at an x value further up. Draw another tangent, and you can see it could go off a little bit from the actual function values that we don't know. So it approximates here. It approximates the y value of a point further up the curve. That's the idea. Well, come down and let's have a look at the idea, the basic notion. The basic notion, the next value, y value, can be estimated using the derivative, which is the slope of the tangent. It uses this idea that the derivative is the slope of the tangent. So let's go back and to our first principles definition. So the value of the derivative, let's say, at an x value is the limit as h tends to naught of f of x plus h minus f of x over h. So if h is very small, so it's tending to naught, then we could say the value of the derivative is approximately f of x naught plus h minus f of x naught on h. So that's the idea here. So if you looked at that, then multiplying, h there, multiplying it across here, and we haven't put that in. So we're going to, I'll just put that here. H is f dashed x naught is approximately equal to, multiplying that across, take f of x naught. Okay, so rearranging that, we get f of x naught plus h is approximately the value of the function at x naught plus h times the value of the derivative. That's the idea here. Or in other words, a y further up the curve, right, from the y value at x naught, can be approximated by taking the y value at x naught and multiplying the value of the derivative at x naught by the small change. So you've got to do very small changes and look at the gradient of that tangent and gradually creep up the curve. Let's have a look at the diagram over here. It's saying if you knew a point on the curve and you knew the derivative function, you could evaluate the derivative function. And what it's saying is, if this gap is very small, the slope function is approximately equal to delta y on h, so that's approximately the f dashed x naught function. So therefore the change in y is approximately h times the f dashed x naught. So in other words, your final estimate of your new position, h further on in x land, is your original y naught plus this extra bit, which is approximately h times the value of the derivative at that original point. So as long as h is small, you can keep estimating the next y. Okay, let's have a look at that down below here. And here it is here. I'll just drop down here a bit more. So here's our y's. Screen clippings here from various places. The problems are going to come from Hayes and Harris publications, so you should have a look at what they've got to say. So if we start here at x naught, and let's say we know that point, that value, we know its x value and its y value. Can we get another point further up the curve? Well, if we don't make the increment in x too big, then we're saying this is an approximate position for the next y value. And we're saying that basically that h is small, this change, delta y, that we're going to add on to the y value y naught, is approximately h times f dash x naught. That's what we're saying. And there it is there. The next y is the y of the original point plus h times the value of the derivative starting at that starting point x naught. So we've got to know a few things. We must know a starting point, and we need to know the derivative function, the derivative. And that's, of course, what we're going to be, we will be given that, and because we can't integrate it to get the actual formula for the function or draw a slope field, we're going to find a numerical estimate of the next y value further up the curve. But it must be in small increments, because otherwise the approximation is going to be very rough. That is h small. Okay, and if it isn't small, we're going to get more and more deviation of the numerical estimate of the y value as we go further away there. Okay, so there'll be a bigger gap between the actual numerical estimate and the actual function value, which we don't know. So you might say, that sounds a bit rough, but remember, we're doing it because basically we can't integrate the function. Think of it that way. Okay, come down and let's have a look at what we do. So here we are. This is my idea here, Huddyism here. We're going to creep up the curve. Why creep up? Well, you can only use small increments in x. H has to be small here. Otherwise, that approximation, because remember it should be the limit as h tends to naught, getting closer and closer, limiting position. Okay, so we've got to keep that small. And then our tangents, here they are, going up, going up, going up, will be estimates of the points on the curve. And you can see here, they're getting a bit wild here as we go away, because we're actually multiplying the error up, aren't we? Taking a second point, which is a bit off, and then doing a tangent value at that, and so on as we go up. So what are we doing? We're going to take an x naught and go to a next one. But in general, we're going to try and find the next x value from the original one. N take 1, and n means this is the next x value we're going to try, and we're going to increase the x value by h, which is small. So our approximation holds. So we're going to change the x value by that. The new y will be the y at the previous n take 1 x value plus h times the function value at the original x. But we've got a starting point, and away we go. So what we're saying is we're calling maybe a point here xn take 1, yn take 1, and we're going to our next point, which is xn and yn. So xn is the original x plus an h, and yn is the original y n take 1 plus h times f dash of xn take 1. That's all in algebraic symbols now. All right, so you get the idea. We're creeping up the curve, estimating the numerical value of the function a little bit further along in x land. Okay, come down and let's have a look. And here, of course, is the fundamental theorem written in a different way. We're saying to get the y value of the next point, it's the y value of the original point, and then if we did it properly, we'd be integrating from a to b of all those small delta x's. Okay, so that would be the exact answer then, if we did that, because we're integrating summing an infinite number, remember, of those delta x areas there. Okay, so this would be the exact value. And we could check our estimate if we were able to integrate the function we're given, but we won't always be able to check that because I'm proposing to you that we will use this Eulers numerical method where we can't integrate the function. So this is going to be a non-integrable function for us. But just check, this is the fundamental theorem, isn't it? Because remember, it's a rearrangement of this, and we said this was the fundamental theorem of calculus equals y of b take y of a. So that's what we're saying. We're rearranging that to estimate the y value further up the curve. Well, we can't always do the exact value using the fundamental theorem, so let's see what we can do by using Euler's numerical approximation here. Okay, so come down, let's have a look at this screen clipping from Hayes and Harris publications. So here we are. Now we can actually integrate this, but we're going to pretend we can't. We're going to find estimates for y of 0.5, starting with the fact that we know the function value when x is 0 is 1. So the point 0, 1 is known to be on the curve. And you must know that for a start. You must know a given point on the curve and the derivative function so that we can use this method. So 0.5. Let's creep up the curve with an h of 0.25. Now that's not a very small h value, it's quite big, it's a quarter, isn't it? And let's do it with just 0.1. And then we'll use the fundamental theorem, done exactly because we are able to integrate this function. Okay, so in our technology land, we'll use technology in a minute, we're going to call x naught is 0 and y naught is 1. So the next x value is the previous x value plus h times f dash x naught. Okay, so here we've got x naught is 0. So this is the x value increment is plus h, and the h is that. So that's the new x. The new y is the original y plus h times the value of the derivative at 0. So we've got to sub that in. So we've got to put 0 into here and get the value 2. So there's our new point. And we'll do it again. So the next x is the original, the previous x plus 0.25. So it's going to be 0.5. And the new y is the y we just got plus h of that. So it's going to be 0.25 times the value of the derivative at that point, which is that. So can you see we're repeating the process, going from one point to another up the curve, always getting the, so we're coming here and getting this one and so on, using successive points. So this is x2, y2, and each time incrementing the x by 0.25 and incrementing the y, change in y, by h times the function value at the previous value of x. Okay, so we're building. There's our second x and second y. Now there's our next x, and there's our calculation to get an approximation for the next y. Okay, so we've got those results for 0.25. Now what about doing it for 0.1? Notice please how this is set out. So step 1 is the starting value for the 0.01. And we're going up in 0.1s, so the next n is 0 plus 0.1, which would be 0.1, and now this is the value of the derivative back at naught, which is 2, and then the yn becomes 2. Now we take this yn as our next point, and our next x, we're going up in another point 1. So h is point 1 again, xn therefore is point 1 plus point 1, the next n is point 2, and then doing this calculation on the previous x, so the previous x was 0.1, so here we go, and we get an answer. And so we go on. It's a reiterative procedure. You've got to build on each of the x value, the previous x, times it by the previous x, find the value of the derivative, and that's your increment in y. So you've got the 2 added on there. So you'll have this one, and plus the increment will be giving you the next y here. Okay, so there we have the idea of the whole thing. So we've got to actually have h.1 times this value, so that'll be 0.22, and add it on. Okay, so this is the previous one, plus h times the value of the derivative at that previous value. Then the next one would be that y plus h times the value of the derivative at the previous x value, which would have been 0.2, and so on. So we've got to get our head around this sort of formula. The next n is the previous one plus 0.1. The next y is the previous one plus, don't forget h, I nearly left that out, times f, well, we'll use y's because we've started with y there. So here y dashed at the previous x. So just keep in mind, this is the previous x value. And so we go. So in steps of 0.1 we get that answer. In steps of 0.25 we get this one. So 0.25 is quite a bit different. It's not as good an estimate according to our theory because h was quite big. H is supposed to be tending to naught. So using the fundamental theorem, we could say theoretically up at 0.5 it was a 0 value, and then it would be the integral. This would be an infinite number of sums there, not just 5 steps or whatever. Okay, so we could work that out, integrating e to the x plus 1, integral of e to the x is e to the x, integral of 1 is x, and then subbing it in, we'll have 1 plus that value, and then take e to the naught in there, which is 1, so it's just going to be this value, which is 2.14872. So here, 2 steps, and that was 0.25, versus 5 steps of 0.1, gives us quite a bit of difference. So the accuracy is greater the smaller the h. So here, more steps, similar to upper and lower sums, which is the fundamental basis of all this. More steps or smaller h is more accurate. Okay, so that's important because what we want is actually an infinite number of steps. That's what the fundamental theorem is doing. So this is the best way of doing it. This is the exact way of doing it. We can't get an exact answer because this decimal keeps going. But you get the idea. You're creeping up the curve in steps of small h's, if you like. And the smaller the h, the better the estimate, the less you're deviating with your approximate value of the function at the next increment. All right, so come down and let's have a look at just a couple of problems here from Hayes and Harris publications. And I would strongly advise you to try to do it by hand for a couple of steps and then use programs available on the graphics display calculators, the various ones, graphics display calculator, that's technology there, where you can do many increments quite quickly without having to fill in the table. The table gets quite complicated of what to use to creep up your curve to make that next numerical approximation. All right, so have a go at this. Here they are suggesting you use the fundamental theorem, but of course in any test or exam they could give you a function which is not integrable and ask you to get your best numerical evaluation of the function, create a curve by approximating the next y further down with increments. So we'll get rid of that. All right, so this is an interesting area. So you can actually get an estimate of the function values with Euler's method. So we're nearly coming to the end of differential equations. Remember, we've got a good surprise coming up where we actually have a look at the logistic equation, differential equation. Anyway, I'll show you the answers here now for this one. Okay, for question 1, make sure you get these answers. Maybe do some by hand and then use technology for the repeated calculation. And coming down to question 2, there, same thing there. All right, so good luck with that, and cheers for now.